Consider a spring with one end attached to a wall and the other end attached to a small block. When x is equal to 0, the spring is in its normal, unstretched state. Imagine that we stretch the spring slowly by moving the block to the right. If we do this slowly enough, the block is virtually in equilibrium at all times. In other words, its acceleration is 0. The spring will exert a restoring force on the block, which, according to Hooke's law, will be given by minus kx, where k is the spring constant. The minus sign is to indicate that it is in the negative x direction. In order to move the block a distance x slowly enough that it is effectively in equilibrium at all times, i.e. a constant velocity, the applied force F dashed to the right must be equal and opposite to the restoring force of the spring. The applied force F dashed therefore satisfies our criterion. It is a force that varies in magnitude with position x. It gets bigger with increasing x. It follows that the work done in stretching the spring so that its end point moves, say from some position x1 to another position x2, is given by the integral from x1 to x2 of f dashed of x dx, which is equal to the integral from x1 to x2 of kx dx. This is equal to a half kx2 squared minus a half kx1 squared. Letting x1 equal 0 and x2 equal x, the work done in stretching the spring is equal to a half kx squared. Notice again that this is just equal to the area under the f dashed x versus x graph.